All right.
All right, welcome to CHEM351 exam review. Meant to be shown on Tuesday, March 24th, to be viewed before you take the test, which is test 3. That will be due the next day, that Wednesday, March 25th. You'll have a PDF on Learning Suite. You'll see the whole exam. There'll be a last page there that you'll take off and fill in all of your multiple choice answers, and then upload that file to Learning Suite in the same manner. So I've sent out some email instructions about that, and there'll be instructions on the exam to help you with that. Ask questions by email or office hours and recitations that we have set up on Zoom now. Also on that Wednesday, there's a lot happening on Wednesday, the 25th. Quiz 7 will also be due. Make sure you print that off, do it, and then upload it. And we'll be starting chapter 12, which is the oxidation reduction chapter in the next section, also on that Wednesday. So for test 3, that's what? Chapters 9, 10, and 11. 9 is alcohols, remember? Chapter 10 is alkenes, and chapter 11 is the alkynes. So I have up here ChemTube, which is a useful program we've told you about. It's free, it's available online. It's got a lot of great animations of organic reactions. The one I'm showing right there is the electrophilic bromination of trans-2-butene, and there's also an animation for cis-2-butene. You can see up there that we've got the stereospecific bromonium ion formation from trans-butene gets the trans methyl groups there. And then when you open up backside attack and then examine the stereochemistry, you have to rotate around there. You can see the symmetry. The trans gives what? The achiral meso product. And that's one of the problems I'll work here in the exam review. And also the cis then gives the same bromonium ion with retention of the cis relationship between the two methyls. And then backside opening, you see there's a change in the stereochemistry here. And so this one is the chiral one, okay? What we're showing here is the SS one. There's also the RR one if you open up on this other side. So that's chiral. That gives you the DL pair, the SS and the RR. So that's the trickier part. Remember, we covered that in chapter 10 a couple of videos ago, but I'll refer back to that there. First, I'd like to do some problems with the board here, maybe a few multi-step synthesis problems. These tend to be the trickier ones. A couple of these might be on the test, and there are different ways we can ask you about that. Either fill in the reagents like we're doing here, or give us the product of a multi-step thing. So here, we're asking you, how do we go from 1-butene to this what? 3,3-dichlorohexane. So what can we do there? Well, we notice we know how to do this type of reaction here. How do we form this geminal dichloride product? Well, we can think about this product right here. If we have an acetylene for this intermediate, and what? 1, 2, 3, 4, 5, 6 carbons. How do we convert this alkyne, this acetylene, into the dichloride? Well, we should know that reagent, right? So 2 equivalents of HCl. So kind of planning, going backwards, you can see we can do the hydrohalogenation with 2 equivalents of HCl, and that will give us the geminal dichloride. You can go through the mechanism and remind yourself there of why the second one goes there. With that selectivity, we have that resonance effect of the lone pair on the chlorides. So how do we go from here, which is what? 1-butene to 3-hexane. So what do we need to make there? Well, we can see we can make this bond. And we've got some symmetry here, so it doesn't matter either side. But we would have to deprotonate this terminal acetylene with a strong enough base. And certainly sodium amide would do that. And then we'd have to have what? We'd have to alkylate that with ethyl bromide. So if we have this bromide here, this combination of reagents would give us this intermediate And then over the arrow for the second step, we'd have to show 2 equivalents of HCl. So hopefully that makes some sense. Isaac's nodding his head. He seems to get it. If you have questions on these, work some of these type of problems. That'll help lock in your understanding of the simple reactions and help you see synthetic planning a couple steps down the road. Same thing here. So we talked about last time in chapter 11 a way to do hydration of alkynes with anti-Markovnikov selectivity to make aldehydes. That's the key thing for this problem. So if we can take this type of a intermediate, 1, 2, 3, 4, 1 butane, and if we do what? If we hydroborate BH3 and do our base and peroxide oxidation of the carbon boron bond, and then remember it gives the enol that tautomerizes. Maybe we need to review that a little bit. So your initial intermediate looks like that after the borane oxidation, okay? The hydrogen and the borane went on in a syn manner there onto the alkyne in oxidation and then tautomerization to the final product here. This is the enol form and this is the carbonyl form. So count your carbons again there, 1, 2, 3, 4, yep, that's correct. There's the 4 carbons of the aldehyde. But the question is, how do we go from here, ethyl bromide again, okay, to this right here? Well, we need to form this bond right there. So over the arrow here, we have to put lithium acetylide or sodium acetylide, or draw it as the ionic thing, it doesn't matter. This is able to do, remember, the SN2 type displacement there. Okay, maybe a couple more like this. Just to review this, and then we'll get right into the sample test 3 that hopefully you've taken some time to look at. Let's examine another multi-step synthesis problem. So start with this. We'll usually give you a starting point, and then make this. So that looks kind of complicated. Until you see, there's the alkyne, that's fine. And what do we make here? Well, the ethyl's already there. So we need to make this bond here. And you can see we've got the 2 carbons here and then the primary alcohol. So in a way, this is a simpler problem, but at first glance, it always looks a little trickier. We could have done something else with the alkyne to make this more complicated. I think we worked a problem like that in the last video. But what would we do here? Treat with base. So sodium amide again, or sodium hydride, you can use either one. Remember, you have to use a strong enough base here. You can't use hydroxide or anything weaker than this pK of 25. And then we get the anion there, and then we can add in what? Ethylene oxide, or epoxide, the simplest epoxide. That will form this, of course, and then we want to see the mechanism. The problem's not asking about the mechanism, just add in the reagents. Now when we open up the epoxide, we have O- here. So we have to put in a proton source, quench with water, and that will give us the proton on the end there. So that one is not too bad. How about this one? This one might seem a little trickier. Here we have this primary bromide with cyclohexyl. How do we go from that? Oh, we still have the cyclohexyl, that's not a problem. To this ketone with a methyl group here. Methyl ketone. And looking at that, let's see, we've got to add how many carbons? Here's the carbon from where the bromide is. We've got to add 2 carbons here. That's kind of a giveaway. And how do we form ketones? There's only one reaction we've learned about ketones. And what is it? Very good. It's the alkyne hydration reaction with the normal Markovnikov selectivity. This is different than the hydroboration of the alkyne. So what do we need to have here? We need to have this intermediate where we'd have what? An alkyne right there. And notice that brings in, what, 2 more carbons. And that's what we need. We have these 3 carbons here on the side of the cyclohexane. So what do we need to do to go from here to here? Let's look at that first. Oh, that's the same thing. The lithium or the sodium acetylide anion should form this fine. And then how do we form the ketone from here? What are the reagents needed here? Right, we need water, but don't forget, we've got to add in sulfuric acid, okay? Now, the case of here, our electrophile is a proton, so we'll have this intermediate that will look like what? We'll have the proton on the end there, and we're not going to go through a vinyl cation. We're going to add the water also. And remember, we talked about that. Initially, it's hydronium ion, and then you've got to lose hydronium ion, and you've got to tautomerize. So there's a couple more steps to the mechanism there. Just like hydroboration with an alkyne, we've got to tautomerize. But in this case, to the ketone, we need to put the electrophile on the end, as we do always. More substituted positive charge buildup here, which is trapped right away by water, and then we've got to lose a proton and then tautomerize it we did before. But that would be the product from that one. So questions on that? We're okay. Those are harder problems now. Test 3 is not going to be a bunch of those, but certainly the reactions are going to have to be there. All right, let's do some other problems here where we have the reagent shown, and you have to supply the products, okay? So let's take this alkene, react it first with HBr, and then react with sodium acetate. What product do we get here, and what intermediate? So here we need to know the reactions, right? This goes back to chapter, 10? We're doing hydrohalogenation, hydrobromination, sorry, of a terminal alkene here. So electrophiles the proton, and what do we get? That's right, the secondary bromide, okay? That's Markovnikov addition. Then we what? Have a good leaving group in the molecule, and sodium acetate's what? A charged good nucleophile. So our product in this case is the acetate ester product, okay? Do we need to worry about chirality here in stereochemistry? No, that's not a stereocenter with two methyls here. So just supply the product there. And that one's a little simpler that way. Okay, how about this one? Sodium amide again, and second part is just adding in the 1-chloropropane, and then 2 equivalents of molecular bromine. Okay. So these reagents, you need to know those in a very confident manner, like what substrate, what reagent, and what product. So to keep track of all these reactions, it's a very good way to study. We can look at this first step here, deprotonating that. We'll get that, then we get the propyl group on there, okay? And now 2 equivalents of molecular bromine. Well, we're going to brominate both pi bonds, right? And with the 2 equivalents, we're going to put how many bromides on there? 4, that's right. So the product will look kind of funny here, but we've got 1, 2, 3, and 4 bromides. Count up the carbons, make sure that's correct. I think we've got 6 carbons and 4 bromides in that propyl group. Yeah, so it's combining a couple reactions there that are a little trickier maybe. All right, let's do a couple more like this, and then we'll get to the sample test. I'm sure you've got some questions there, and I'll work some of the harder problems. We'll step through the exam, pull it up and have it visible when you watch this video. Hopefully you've worked enough problems in the chapter problems to have this down. So let's do this first one here. So we've got an alcohol. First we're going to react with sulfuric acid. So that's going back, what, to chapter 9, right? The alcohol reactions. Then our next step here is chlorine and water. And then sodium amide. Now this is 3 steps, but these are all reactions we know. So just do each reaction individually, and you should be able to arrive at the correct product. Let's see if we can do it, right? So what do we get? Sulfuric acid and an alcohol. What type of reaction is that going to be? It starts with a D. What is it? Very good, dehydration. Okay. And so if we pull water off there, we're going to get cyclohexene. okay? And now if we react with chlorine and water, what's that? That's the chlorohydrin reaction. It'll form the same chloronium ion, the 3-membered ring with chlorine and a plus charge. But then the better nucleophile, and this is a solvent, water, that's going to open this up. So what are we going to get? We're going to get chlorine, and we've got to have some stereochemistry involved here. This is the chlorohydrin, an alcohol with chlorine. And notice I draw this trans. Why did I draw it trans? Because the chloronium ion is bridging here, right? On the same face, plus charge there on the chlorine. And now we've got chloride, and we've got water in there. And water turns out to be the better nucleophile. I'll draw it attacking from that side. I could draw it attacking over there. We need to comment on that in a second. This will give us what? A DL pair. Both of them are trans. The other enantiomer are not shown. We've got chloride back and OH in the front. Make sure you can verify that. Attacking either side from below. Okay, we'll get you to either one there. It actually doesn't matter because this next step does what? Sodium amide. What's that again? That is a strong base, right? Where is a proton that's acidic enough we can take off? Oh yeah, right there on the alcohol. So that will give this intermediate, after we treat with strong base, what? O minus and chlorine. Right there, trans to it. What do we set up to do here? How do we get to this final product? 3-step sequence. That's right. We'll use this as a nucleophile. And there's our leaving group, right? And backside attack, right? Well, what? Invert that stereocenter. And what do we get? We get the epoxide product. You can draw up or down, it doesn't matter. It's achiral now. But the intermediate here leading to it is actually chiral. Okay, so from either one can lead to that. And you can verify that. But that's the product there if we have a leaving group right next door to a charged nucleophile. Okay, that's a fun sequence there. It's one way to form an epoxide. We'll see other ways to do epoxidations of alkenes in chapter 12, so stay tuned for that. But yeah, that's a harder problem. Those 3 reactions you should be able to follow, okay? All right, let's do another, well, a couple more of these. We'll get to the test eventually. Hopefully working these harder problems is helpful to you. And if you've done enough of the problems on your own, you should be okay. Let's see, let's take this epoxide. It's got a stereocenter and some issues there. We have a tertiary position here, secondary position there. That might be important for this reaction coming up. Sulfuric acid and methanol. Maybe that's not a combination you remember, but mechanistically, I think you can figure that out. The strong acid will protonate the epoxide, and then what will happen? It'll open up in a certain way. Then we have a neutral nucleophile now. Okay, so some different things there. But let me get the whole sequence up here, and then treat with sodium hydride, and then treat with this bromide. Okay, and what is the product? Again, a trickier 3-step thing. Well, these are really combined here. We're going to deprotonate something with a strong base. We could have used sodium amide here where you're showing sodium hydride, that's okay. And then we're alkylating an anion probably. That's the way to look at that. This first step here though, what do we get? We get protonation of the epoxide, it opens up, and we get the tertiary carbocation. Now I'm kind of jumping ahead of there in the mechanism, but you should remember that one. The first step is protonation, and then we break it that way. Why do we break this bond and not this one, the epoxide? That's right, because that is the tertiary carbocation under the strong acid conditions with a neutral nucleophile, okay? So where does the nucleophile go? It goes here, either top or bottom. It'll give a mixture. You don't need to worry about that. So yeah, in fact, let's just leave it like this for now. It'll be a mixture of what? Not an enantiomer, it's actually diastereomers. This stereocenter is fixed right there, okay? So it'll be a mixture of diastereomers. You can draw both of them with the methyl down, the methoxy up, or reverse there, it doesn't matter. And then what's the next step? Well, we're going to take off this, form an O minus, and then react it with that, right? Here's a charged nucleophile then, after treatment with the sodium hydride, okay? Primary leaving group, that's good for what type of reaction? SN what? 2, very good, okay. I think we're unanimous on that. If not, double check that. So what's our final product here? We have this methoxy ether there, methyl group mixture of stereocenters there, and what's here? We have this stereocenter fixed, and what? It's now an ether also. So we form this diether product, where they're both different there. So that's a little trickier problem too, I think. The next couple ones I want to show you, I think, are a little simpler. I'll draw them both out here. They review some other types of reactions. You see a lot of SN2 reactions coming back. Those are very important reactions. Different conditions there. We've done ones similar to this in the alcohol chapter. Treat first with tosyl chloride and pyridine, and then treat with sodium methyl sulfide. Okay. Or treat this first with SOCl2, remember the name of that, thionyl chloride pyridine, and then treat this with that same methyl sodium sulfide. Thank you. Yeah, I left that off. Yeah, it's methyl sulfide with sodium. Yeah, I did that. Okay, let's see if we can do those two, and how might they be different. Let's do this top one first. We put a tosyl plate group on there. We're going to get this OTS, and we're going to retain that stereochemistry. You don't need to know the mechanism of this, but you can kind of see a lone pair has to attack the tosylate, which is that sulfonate group. I drew it out before, it's in your book. Chloride eventually comes off. Pyridine is basic enough to take that proton off, but that stereocenter is not touched, okay? That's a secondary leaving group. And we have what type of nucleophile now? We have sodium sulfide, this methyl sulfide. That's sulfur, negative charge. That's a good nucleophile. So what type of reaction are we going to expect here? Again, SN2. And what? We got stereochemistry there. The tosylate's a good leaving group, just like halide. So we're going to invert that center. We get the sulfur methyl sulfide. Okay. So that'll be our product there. We treat first with thionyl chloride here. Pyridine. Remember, we form the same sulfur type of intermediate here. Chloride comes off as a leaving group. But in this case, we don't form a stable intermediate. This becomes a good enough leaving group, and chloride is actually formed as part of the mechanism. And chloride, remember we told you with thionyl chloride, secondary alcohols will give what? The chloride with inverted stereochemistry. That also works with primary alcohols, but with secondary alcohol, it'll give this inverted product. Now we have this, it's the R thing from the S stereocenter. And now the same conditions here. Treat with the methyl sulfide anion. And what do we get? We get the same methyl sulfide, but we get a second inversion. Okay? So one inversion here with the thionyl chloride, another inversion here, which what? Retains that stereochemistry as S. So 2 inversions equals what? Net retention, you could say. It's retaining that stereochemistry. Here, because the tosylate formation retains the stereochemistry, and this one inverts it. One inversion gives what? An inverted stereochemistry to the R product. So this kind of combines some of this reactivity from way back chapter 9, in case you don't remember it, with these types of reactions. Let's do one more set of reactions here, and we'll move over to the other board. And this shows some other utility reactions. So we have an alcohol again, going back to chapter 9. PBr3, phosphorus tribromide first, then lithium acetylide. Okay, our charged good nucleophile here. And then boron, borane and base peroxide workup. Remember borane, you could use 9 bbn also. That actually improves the anti-Markovnikov selectivity. Either way, or just show borane like that. That's fine. So what's our first step? Phosphorus tribromide with a primary alcohol. That's a good combination to form what? Form the bromide. Primary bromide now. Good leaving group. Now we have a charged small nucleophile, which is what? Perfect for yet more SN2 chemistry. That will give us this new acetylene, terminal acetylene, and hydroboration of that will give us the vinyl alcohol, but at what spot? Will the alcohol be here at the 2 position or at the 1 position? Remember, borane gives anti-Markovnikov selectivity, so we'd expect the vinyl alcohol out here at the 1 position. Remember, there's another step there. It then does the T process, tautomerization, right? And so our final product here is what? Not the ketone, but the aldehyde, okay? So notice the transformation. This alcohol, we add 2 carbons to it, and then we do the hydroboration to see the 2 carbons added there, and then the aldehyde. Okay, let's see. Let's switch over to the sample test and go through that. Get that back up there. Hopefully you can pull that up. Hopefully we'll see it well enough here up on the board. If not, make sure you got the document open on Learning Suite and practice it first before you look at this video maybe. I'll kind of go through it and examine some of the harder problems that I think the students, have asked about before. I've had some people email me already with some questions about it, so I think I prepared enough to point some of those out. So let's just go through it. I'm not going to work every one, but I will go to the board and work some of them. So we'll kind of go back and forth here. A lot of these are just naming and definitions here on the first page. Here's the tosylate formation that we just went over there with that problem. So tosylates are formed from secondary alcohols using tosyl chloride pyridine with retention of the stereochemistry. So that's that first part of that one. Some of these are just kind of definitions of the different reagents. So you should know what thionyl chloride is, SOCl2. So, there it is. It's not this reagent, that's actually phosgene. This is a different thing with a carbon there, and this is a phosphonate. This is a bigger thing here. So this is thionyl chloride right here. Some of the properties of alcohols, number 5 there, which alcohol is most soluble in water? How would you figure this out? Primary alcohol, primary alcohol, primary. Not the tertiary. Remember we said hydrogen bonding is weakened if there's a lot of branching near the OH group. So we're talking about what? In water, we're going to hydrogen bond, be a hydrogen bond donor and acceptor. If this is hindered, that will make this less water soluble. Butyl alcohol is not very soluble in water. The primary alcohols are, but we've got then what? Ethanol, we've got a 5-carbon chain, and then what? A 7-carbon chain here. So then we have the hydrophobic effect. So it's really 2 things here, the branching and the length of that nonpolar chain. So ethanol will be the most soluble one. Hopefully that's clear. Next page here, definitions, carbocations. The one with branching next door is the one that will shift here. So that one's not too bad. Which are the primary alcohols? So you can figure that one out, I think. Electrophilic addition. Remember for chapters 10 and 11, that's what we're talking about here. The alkene acting as a nucleophile. All the reagents are electrophilic, partially positive or a full-blown positive charge. So that's what we're talking about. The alkene acts as the nucleophile. Electrophilic substitution, we're talking about what the nature of the reagent in that case. Addition of bromide to an alkene in water gives a bromohydrin. That's kind of a definition of that key reaction. I think that's reaction number 4 in chapter 10, if I'm correct there. Bromonium ions, this kind of goes together with it. The intermediates in the addition of bromine to an alkene. Okay, a bromonium ion is that cyclic three-membered structure with bromine with a plus charge. So you should remember how that's forming there. The lone pairs bridge over from the intermediate carbocation at my point. Then we have a naming one here, which is giving the alcohol the lowest priority. That's number 1. Then everything else is named in relationship to that. So this is the 1-all, 1, 2, 3, 4, 5, pentene, 3-ene, yeah. And it is Z here. The highest priority groups on the two sides of the alkene are together. So it's zusammen, the methyl chloride here, and then this part. And you keep going down the chain to break the tie. You examine each two groups on each two sides of the alkene to determine if they're together. Top priority groups, that's Z. They're across, that's E. Okay, this page here, there's a couple other trickier ones. I think these are okay up here. 15's a little tricky. It's got a couple steps maybe. It gives you a compound here and you have to convert it into this, which is a chlorohydrin. Okay, so you should remember the chlorohydrin reagents. You can just look for those and say, oh, there's chlorine in the water. So you can narrow it down just by looking at this arrow right here. And it must be that. And then you can verify, oh yeah, POCL, phosphorus oxychloride and pyridine, will what? Do an elimination of an alcohol to an alkene. Secondary alcohols work very well. So this will give an intermediate of what? Cyclohexene, and then chlorohydrin formation. All the others do other types of things that aren't the right combination. So if you're picking D, for example, borane and peroxide with an alcohol, that's not a combination we've covered. We've only done hydroboration of alkenes and alkynes, okay? So you can kind of match up the substrates and the reagents you're familiar with there. This is an interesting one, 17, calcium carbide. I failed to mention that when we talked about chapter 11. It's in your book, actually. Calcium carbide, and I give you the formula, calcium. And calcium, if you have the periodic table, it's in the second row. So it forms a +2 cation. Sorry to reorient there. And then we've got the acetylene, but with both ends deprotonated. That's actually the structure of calcium carbide. It's actually a mineral material that can be mined, pulled right out of the earth. It's a solid rock-like material. You have to crush it up and at the factory treat it with sulfuric acid. And what will you get? You get the strong acid protonating these two ends of the carbide, and eventually you get what? Acetylene gas bubbling out of the solution. So historically, this is how acetylene gas was formed. Welder's gas, it combusts, burns very well, has a very high temperature flame, but it comes actually from calcium carbide, which is an interesting alkyne reagent. I showed you some drugs also that were on the overheads in chapter 11. You can look at those, but yeah, calcium carbide. Sorry, going back up there to the sample test. Let's see, tautomers, another definition there. Pick the one that has the right thing here. Yeah, all the others kind of don't make sense at all. Enol keto isomers relating to proton interchange. So that's, you know, the initial vinyl alcohol going to the aldehyde or the ketone by just transferring the proton. So that's what we mean there, and D is the answer for that one. All right, last page, those two are fine. The reaction chart, these are always a little tricky, you could say, you know, tests your understanding of each individual reaction. We have a handful from each chapter now. We have the 5, you know, H reactions applied both to alkenes and alkynes. So that comes out to about 10. And then we have 8 or so of those alcohol reactions. So make sure you understand those and how we can convert those into other things. You got the alcohol reaction up there. You got the epoxide reaction we just talked about, very similar to the one we just worked on the board right there. Retaining the stereochemistry for the alcohol, the S form at the secondary position, This is sulfuric acid methanol, so it gets scrambled stereochemistry for the methyl ether spot. Then we got hydrobromination, that's fine. Make sure you show the Markovnikov product. Don't draw the minor primary bromide there, we'll mark off points. And notice that is chiral, that's a stereocenter. So you can say DL or draw both R and S. If you don't define it, make sure you say DL or RS, whatever there, don't leave it unlabeled. This is hydrogen formation, and they are the anti ones there, and that one's also chiral. This one here, this one's a little bit tricky. You've got the hydroboration reaction, where boron now is the electrophile. It goes at that secondary spot. Hydrides delivered from the same face. Okay, so then boron and this methyl group are opposite of each other. Okay, and then the oxidation goes with retention of that stereochemistry. So you get the secondary alcohol and this methyl group next door in the down position. And that's chiral also. You get the two trans and antimeres there. Okay? We're going to talk about this one. I think that one's okay. And this one is that same type of reaction. We just worked on a synthesis problem like that, where you got this alkyne here, hydroboration, anti-Markovnikov, and then you get the vinyl alcohol, tautomerize what to the aldehyde in this case. So I think those are okay. Didn't want to go over those too much. Let's see, the naming, the nomenclature, we'll try to keep that as simple and straightforward as possible. If you follow the rules there, you should be okay. Alkenes, alkynes, and we can have what? Alkenols, and we can have alkynols. If there is an alcohol in there, make sure the alcohol always gets the lowest possible number in a chain. Wherever it is, it doesn't matter relative to other things. If it's in a ring, the alcohol automatically gets number 1, and just number everything relative to that. Here's the one we were just looking at in CHEM351. So we can look at this again here, and what you see is the trans 2-butene. We're doing the halogenation, we're chlorinating it, and we get the intermediate chloronium ion, which retains that stereochemistry, the two methyl groups being trans. And then when the chloride anion opens up the chlorinium ion, we pop that open here with backside attack, which gives what? This anti-relationship between the two chlorides. And that's what? These are meso, okay? This is the same thing. Either attack from the other side gives that same thing. You can see a center symmetry here, or rotate around, and you see the near plane relationship. So trans of a symmetrical alkene with chlorination here. This is symmetric, the ends are the same. The stereocenters are reflections of each other. What? This is the R and this is the S. That's okay. There's a center of symmetry, or you can see conformationally there's a near plane. So achiral product there. If it's the Z, that same chloronium ion, backside attack, you see the two methyl groups still showing the cis relationship there, and the two chlorides showing the anti-relationship of the opening up of the chlorinium ion. And then you can open up on either side, and that will give you either the RR enantiomer or the SS. And again, if you assign stereochemistry, you'll begin to see this, right? RS or SR means what? Meso, if there's symmetry there. The stereocenters are reflections of each other. If you see RR, you know what? That's the chiral one, and its mirror image that's non-superimposable will be the SS, okay? So equal probability you can get either one. So that's the chiral one, it's the achiral one. This is a trickier concept. I've worked out a couple different ways. We'll go back to the YouTube at the end and maybe remind you of that. You can work through that and see that. I'll leave it there right now. Let's finish the rest of these problems maybe. And this is a different way to ask synthesis problems. And we can, accommodate these for multiple choice, where we have different choices, A, B, C, or D. So these can all be converted into multiple choice problems. So my exams normally are only 20 multiple choice and then these write-on questions. But now your exam will be what? 40 multiple choice questions. Okay, so work through it with your scratch paper, models, whatever. It's closed book though, so you've got to practice enough to get this down. Let's see, some of these I think are pretty straightforward. We've been working some similar ones. Yeah, I mean, that one's fine. This one, the tosylated version, yeah, that's fine. And this one here, Pockle, without migration here. If you did this alcohol right here with sulfuric acid, you'd get that migration, remember, and then loss of water, and you get a different product. You get that rearranged product with the shift, remember. Here, we've been doing this one here, which is hydration of an alkyne now, to get the ketone. And then this one right here, hydroboration, to give the alcohol product, the primary alcohol, and then deprotonate that primary alcohol, and then alkylate it with ethyl bromide to give the ethyl ether. Okay? So I think those are not too bad either. Now, this gets a little worse, of course. So here's a harder mechanism problem. And we'll work a couple of these. I've got a couple other harder mechanism problems. So Isaac, we may go back to the chalkboard over here if you want to reconfigure things a little bit. And let's see, we'll work a few harder mechanism problems to finish off our discussion today. Yeah, let's start over here. Got a few minutes more. Do a couple of these harder mechanisms. You can ask mechanism problems on multiple choice format. We'll give you a couple different choices for like the next step, or how the electrons are pushed to form this next intermediate. So there's a couple things we could show there. I like this problem because it gives you the opportunity to really test your ability to follow what's going on here. We're going to give you the product, which is this cyclopentane, and then this six-membered cyclic, ether here. And we're starting from this cyclobutane, and you're told here that the only reagent is sulfuric acid, which is dehydration conditions, or at least forming carbocations. Now we could start out by protonating either alcohol here. Which one do you think will be productive on this pathway? This one will lead to a primary carbocation? No. You can protonate there, that's reversible. But once you protonate here, with the plus charge, look, you can form this more stable secondary carbocation. Now that's not the end of the story, of course, because once you form this secondary carbocation, what can occur now? Well, you can see you go from a cyclobutane to a cyclopentane. So you know you've got to do a shift of some kind. And so let's go ahead and do this shift, where we just bring this pair of electrons out of this sigma bond and migrate over here. That will give us what? This new arrangement there. We'll have our plus charge move over. And what we have, how many more? 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So I think we got the same number of carbons here. Oh, no. We may have flipped the orientation of that over a little bit. So what we had 4, 5, 6, 7, 8, 9 carbons. So here's 4 or 5, 6, 7, 8, 9. Yeah, I think we're okay there. Does that look right? I think so. And now this one's secondary again. But why would we go from a secondary to a secondary? We relieve the angle strain in the 4-membered ring. And so this is a strain-free now, 5-membered ring. That's okay. But we can do another shift here that's consistent with the product. You see we have this carbon here, which is what? Tertiary. And so right now, if we attacked our alcohol over here, we wouldn't give that same type of product. But if we can do this shift here, look, we get this cyclopentane with now the carbocation right there at a tertiary spot. So the next part of the mechanism is that, okay, that 1-2 shift of the hydride to give that. So we have initially a 1-2 alkyl shift, okay, and then we have what? A 1-2 hydride shift, okay. So what migrated there was this hydrogen with its pair of electrons. And you see that wipes out the positive charge there. There's now 2 hydrogens there, and it creates the carbocation right there. So how do we get to the final product? Well, we'd have to cyclize here. And there's a couple things we could do there. We could pull a proton off either side and give the alkene product. I think that's some of the minor things there, looking back at what was shown on the test. No, I think it no, it gave you a couple, did it give you some minor, oh yeah, it did. Oh, it gave you a bromide. Oh no, wait a minute, we're using HF or HBr. Which one are we using here on this problem? Okay, I think on the sample, oh, I've done this problem a couple different ways. I think on the sample test, sorry, it is HBr. That would be identical up to here, and all this stuff. And you can see where a couple of the minor products have formed there. Let's form maybe one of the minor products from here. So we could lose this off of here, and that would generate the cyclopentane with the alkene right there. And that's one of your minor products. Yep. And you're told C and B are minor there. The other one is if bromide, which is in there, if you're using HBr, could attack there, and that would give you this bromide product. So it would have, be a minor amount. Bromide's not a very good nucleophile. Better nucleophile is actually oxygen here, more stable bond, carbon-oxygen bond. So if we attack there, notice we'll get the six-membered ring forming. And it's got proton on it right now, so it's another step in this mechanism, right? So we need to take off this proton either with water. We generated water at a spot early on there, so let's use that. And that will give us the final major product in this case. So this is obviously a harder problem, mechanism problem. We give you the final product. We're not expecting you to come up with it on your own. And your job is just to do the steps that correspond to the normal things you've learned to get from that starting material to that product that's shown. So hopefully that one's okay, working through that. Sorry I messed up with the sulfuric acid versus the HBr. The principles apply the same there. Let's see. Another problem here. Let's do maybe two more, then we'll wrap up. So let's see. A couple harder mechanism problems. Again, these review a lot of great principles, I think. Oh, and this one reminds you of another reagent we may not have mentioned yet. We're going to take this alcohol, which has a cyclohexene on it. We're going to react it with NBS. Now, what is NBS? And then we're going to react it with potassium tBetoxide, and we're going to get this product. And now your goal here is just to provide an electron pushing pathway that gets from the starting material to now this bicyclic product. And it's an ether, right? What is NBS? That's the first thing to remember. N-bromosuccinimide. And I don't expect you to remember that or how to name succinimates. We haven't done that. But the bromide is on the nitrogen here. So this bromide is what? Charge or partial charge. It's partially positively charged. You can think of this as just like this, okay? Just like bromine, where you have the partial positive end and the partial negative end. And any that's nitrogen's partially negatively charged, you can pull these electrons out here, and what? Then you have a negatively charged nitrogen resonance stabilized on these two carbonyls. That's why this works. So let's go ahead and do that. Draw the mechanism here. We'll have bromonium ion. And I'm going to form bromonium ion on the top. Why? We'll form it either on the top or the bottom. There's actually equilibrium going on there. Let's see, it's away from this alkyl group here. And plus this alcohol now that we want to bring in and open up the bromonium ion, if it comes from the bottom face here, you see it will invert the stereochemistry that you're asked about in the product there. Okay, so let's go ahead and do that. Let's bring this in. The backside attack. So that's just like, water from the halohydrin reaction, but now it's from an alcohol. So yeah, it's different than your typical reactions. Gives a little bit different product, but it does lead to the eventual product there. We've got bromide, we've got that carbon in the back, and this oxygen. And it's got its proton still on it, so you draw that intermediate, and then what takes this off here? Well, you've got this nitrogen, this negatively charged, from your succinate imide. And you know, if you use any base, I think you got full credit for this when we gave this before on a test. We did get this problem on a ride-on, problem on a test before. If you use bromide to take this off, I think you still got credit for this first step. We're just working on the first step, NBS, okay? So let's see, what can we do? Take this proton off, and what are we gonna get? We'll get the product there. You know, let me get some more room here. So, yeah, this one's a little harder. It's a two-board mechanism, I guess. So what do we get there? Take the proton off. We'll get our bromide still there, and our ether, the down position right there. All right, now TB toxide. Okay, so that's our first intermediate. What's TB toxide going to do? Well, it's O-, the big terp-butyl group with potassium salt. Okay, don't forget it's O-. It's a base. It's charged. Could it be a nucleophile? No, it's bulky. It's got the terp-butyl group. Remember, it always does what type of reaction with leaving groups? Very good. It always does E2. And that's what our product is, an alkene product. And the alkene needs to be right here. Okay, so we can just take a proton off there, TB toxide minus, and look, they're anti to each other, and we need to analyze that because how come we're not pulling this hydrogen off? Okay, how come the alkene's not forming there? That would be the more substituted alkene, right? Trisubstituted alkene versus this spot is a disubstituted alkene. Remember we told you before, the more substituted alkene is, the more stable it is, the more likely it is by Zaitsev's rule. But it forms here. That gives you the product up there. How can we better analyze this? Well, I already mentioned it. And I'm showing this hydrogen that's down right there. This is another hydrogen that's up right there. Let's maybe draw a three-dimensional view of this intermediate. Oh, we're going back to the dreaded chair, aren't we? We have a cyclohexane, so let's have the chair there, and our bromide is going to be up right there, and this hydrogen is down. There's another hydrogen right there. Let's see, where is everything else? We've got this oxygen down right here, hydrogen in the front, and the rest of that right there. That is this in 3 dimensions. Okay, verify that. Does that look right? Isaac's nodding his head, thumbs up. That is it. And you see the chair relationship. Bromide's axial, oxygen's axial. And the alkyl group, this methylene here, is equatorial. That's a good thing. This conformation has what? This, which is where we're going to take the proton off, release those electrons, and do the E2 elimination to give to the alkene product right here. Okay? Is this the major conformer? Well, you know, you got full credit on this if you just showed TB toxide pulling off one of these. So I'm giving you a little bonus here with the conformational analysis. This is in equilibrium with what? It's ring flip guy, which would have this chair here with now the bromide equatorial. So if you ring flip this part, this other hydrogen's right there, right? That's the one that's now axial, you could say. So these hydrogens are flipped now, axial equatorial, and this one, we need to look at where the ether oxygen is. It's right there. And then we've got the rest of the other ring right there. Got that hydrogen there. And that was the other one we were thinking about pulling, right? Notice it's equatorial here or axial here, but in this conformation it's axial and the bromide's equatorial. So the one that's set up for the anti-staggered arrangement for the E2 is best in this one right here. Okay? This one is forming. It's in equilibrium with that one. Notice we have the bromide equatorial, the oxygen equatorial, but look at the methylene's axial. So, you know, they're probably close in energy, but then this one reacts fast to get the observed product, okay, which is up there in that corner. Show them that product again. Yeah, to verify that. Anyway, so that was kind of a torturous tour to go through that, but I think it's a good mechanism to keep straight. It reminds you of the NBS. You can always use NBS in place of bromine, Br2, okay, for reactions, for that bromohydrin reaction, NBS in water. That's a good one to do that. And also do the bromohydrin and alkynes. That combination also works. But okay, let's do one more. I think this one's related to one in your homework that's a little tricky. So let's see if we can do one more and hang in there. Exam review. Again, email me questions if you have any more on the homework, which was due on Monday. So you already turned in your homework. Maybe I could give you some hints on the quiz 7, which is due tomorrow also on the 25th. Yeah, we might have a minute. Maybe we'll show you a little bit of that. But this mechanism here, so we have an alkyne and an alcohol, and we have sulfuric acid, and we have water. Now that's a combination alcohol. You could picture, oh, this could just dehydrate right here. But they give you a different product here. They give you this unsaturated aldehyde product. And this problem is push electrons, show intermediates leading from that alkyne alcohol to this unsaturated what? Aldehyde. That's the challenge here. So what are we going to do? Well, let's go ahead and protonate. That first step, let's go ahead and lose water. So that would be a secondary carbocation. It's resonance stabilized by the alkyne. And if we lose a proton here and eliminate, we just go to the E9, right? But something else happens here. Water can actually attack, push these electrons over, and we get this kind of crazy looking thing here, which has water attacked on the N carbon here, with pushing the electrons over. And that's kind of the resonance structure of this, right? This is like that allylic resonance we talked about before. With an alkyne here, it's called propargyl resonance. This is propargyl alcohols. Don't worry about the term. But that means this carbon here on the end is what? Positively charged. If this is positively charged, we have a secondary carbocation in resonance here. And if we attack this side with water, look, we've got an oxygen now on the end. We've got a methyl group here and an alkene already here. So we're already halfway to this product, okay? What do we need to do? Take off the proton. That will give us this enol, okay? And we've talked about that before. When you have two double bonds right next to each other, or accumulated right next to each other, that's called an almene. We'll say more about these polyenes later in 352. Don't worry about the term now. We're just practicing pushing electrons anyway. So this is an unusual reaction compared to the standard alcohol dehydration. But we get to this enol now. What is this? This is just tautomerization. And we can do it, systematically here. Let's take more acid and protonate that. Bring the lone pair down. I'm kind of combining a couple steps here. We get this. With that hydrogen on it now. We get this. You see there's our carbonyl double bond. Now we have a plus charge on oxygen. You could do that stepwise, have the plus charge here first, and then bring the lone pair down to give the aldehyde carbonyl. And then what do we need to do? Take off that proton with water, and that will give us the product. Okay. So it's not too bad, but it is a tough mechanism problem. Okay? There won't be a bunch of these on your test, don't worry. If you practice some of these, you'll gain some experience and help out of that. All right, the last minute, let's give you a little help on quiz 7. And you can get help on quiz 7, of course, office hours. We'll be Zooming that on Tuesdays and Thursdays. You should have gotten an email about that. Let's see this quiz, and let's see if we can show you a couple things about it. Where is it? Oh, there it is. We've got a problem of forming limonene. And limonene is this guy, right? And it's got an alkene, and it's got a stereocenter right here. Okay, so that is a stereocenter right there. Put a star by it. That's limonene. It's a little terpene compound, 10-carbon hydrocarbon, essential oil compound. And it comes from this thing, which is a 10-carbon diene, which has pyrophosphate. Now on your quiz, you see that. I'm not drawing out the whole phosphate thing now. But if this ionizes, and you're given that as a hint in the quiz, you'll form this allylic carbocation, right? We can draw some resonance structures of that, one of which would be this, where then we have the carbocation right there. And notice I'm switching the conformations here. I'm also rotating around this bond right here. And that puts you in a position, I think, to form limonene a little more directly. And I'm not going to do the rest of the electron pushing for you. I think you can do the rest from there. You're going to have to push these electrons into this double bond, or draw another resonance structure here with the plus charge out here, the double bond there, which you see in the product. And if you form this bond right here, you'll have a carbocation there, and the rest is history. Then you have to comment about the enzyme. What's the enzyme doing? So the enzyme in the plant is actually catalyzing the process of this pyrophosphate into the limonene. And what are you doing? Well, you're helping to ionize this, stabilize that. You're helping to get the new carbon-carbon bond to form. Then you've got to take off a proton here to get the alkene there. So what could the enzyme do there? And plus the stereocenter. What is it about the enzyme that might control that stereocenter? Say something about that. You'll get full credit. And maybe that's it. I think you can figure out oh, problem 3 is a little tricky too. Let me give you a little help on problem 3. I don't know, this is a multi-step synthesis problem, and you're told to start from isopropyl alcohol and get this aldehyde. Show your reagents and the intermediates. You're not going to do it in one step, but you're going to have to go from that alcohol to that. And the first thing to look at is you have the alcohol at the 2 position here. You don't really have anything at a 2 position here. You're going to have to functionalize that isopropyl alcohol into something that you might be able to put on as a 3-carbon unit, right? Use all 3 carbons of the isopropanol. And then you need to put on 2 more carbons to make a total of 5. And then you got the aldehyde. And you already know that's got to come from this, right? We only know one reaction to go from here to here. Show the reagents for that. This gives you an idea of what to form here then, right? So your step here would be what? From some sort of a leaving group there. Can we go from this secondary alcohol to that? That's kind of the tricky part. And you know how to do this, right? You know those reagents? Now how do you go from that to then having a primary leaving group over here? You want to think about hydroboration again, right? And then converting into some sort of leaving group. I'm not giving you all the details there, but hopefully these hints will help you out. So this is for viewing again on Tuesday, the 24th, and this quiz 7, isn't due until Wednesday, March 25th. So we'll ask questions in the recitation, which will be zooming or zoom into my office hours, and we can help you out with more things. So good luck. Keep studying hard. Your efforts will be richly rewarded on this test. Do your best there to prepare and stay ahead with the problems. And we'll see you next time. Very good. Thank you.